Hello and welcome to this webinar on the language features of version 18 in depth. It is actually the second webinar on this subject, and I will be continuing every other Dyalog webinar with the new language features of version 18 interspersed with webinars on other subjects. So that means every 4 weeks. This is a condensed overview of the new language features in version 18. In the previous webinar that I held, which was 4 weeks ago, where I went over these 4 first features, and today, which you can see on the Dyalog.tv/webinar, today I'm going to continue with the next 3 in the series, next 3 of these features. So without further ado, the first one is the constant operator. It's actually a really simple thing, but it's quite versatile. Until now, we have had the Dyalog idioms, which are particular spellings in expressions and functions that are highly optimized. And they don't actually evaluate what the code says, but rather they are special cased to go directly to the solution. And so we've had these 2 idioms, braced 0 and braced 0 each, which would replace any argument with a 0 or replace all the elements of the arguments with a 0. And what we're doing here is we are generalizing this to an operator, which is using the same symbol as the commute or swap selfie operator. And that allows us to have high performance on replacing any arguments with a constant, hence the constant operator. Why are we doing this? Well, the notation is actually pretty obvious, and it has some benefits, especially when you're writing tacit functions. And then it also allows you to write certain things in nice ways, whereas before you would have to make it a bit complicated and not so obvious. So it helps some on the reading as well. I'll go through this. The overall syntax, again, is really simple. It takes a constant, an array, and then it returns that no matter what. So you can use it dyadically or you can use it monadically. When it's monadic, you don't need to separate it, even if it's inline separated from the arguments, of course. And it is as simple as just returning what you give it. So that means if you give it a ref, then it will return that same ref. It doesn't make any kind of copy of some sort. It just returns it. Now, it might seem strange, but we have actually had something similar for a long time. The idea of treating an array as a constant function, a function that always returns that same constant. So we consider our 3 trains, forks, and certain cases of the at operator in use. And you can give it a constant function, of course. It's just like any other function. But we also allow just using that that array to mean the function that returns that array. So then you could see it as just removing the braces that are just redundant here. So an array in certain contexts works as a constant function. And what we're doing here by adding this operator is we can start off with this constant function, and then of course if we swap the arguments or move the right argument over to also be the left argument, that doesn't make a difference because the function always returns the function always returns the same constant. And now we simply replace the braced version with the unbraced version. Just remove the braces, and here we have it, the constant function. In fact, when you use braces like this for a constant function, you can run into certain problems, and I'll come back to that later. So there are cases where you can't just do that, and you want to use the unbraced form, or just using an array for a function that returns its value. Where it really shines is in the combination with various operators. So here, for example, we can take this constant and replace every element. So that's constant each. Or we could do it on a higher rank array, and it would give us a similar result. And what's interesting here is, of course, that when we get a random number, so 7 of course is just an example, then that value, that array, is a constant that's being used for every element in the 2x4 array. If we had put braces around the question mark 9, then the question mark 9 would have been evaluated over and over again, and we would have gotten different values in each place. And we can do it the same thing with rank here. So what's happening is we start off with a 2x3x4 array. So it's a 2-layer, 3-row, and 4-column array, and we are putting a constant, which is a scalar, at replacing every rank 1 subarray. So you can see a rank 3 array as a rank 2 array of rank 1 arrays, and so what we get is the remaining shape, the 2x3 shape of scalars. So that's our 2x3 matrix we're getting back. Of course, endless possibilities using this. The other benefit I mentioned was preserving the visual order in trains. And here's an example. Let's say we have this expression, or the body of a function, which is a sum, and then we cube that. Now, let's say you wanted to go test it and write this as a train. So you might think that, oh, okay, we have a function. Instead of explicitly mentioning the arguments, we just say the plus. So that's and then we raise that to the power of 3. But this doesn't work because you can't have a constant, an array, as the rightmost tine of a train. That would just become a normal APL expression, and that would be the complex conjugate of e to the power of 3, not at all what we want here. So there are various workarounds that we've had to use until now. You could flip the arguments around of the middle tine, that puts the 3 on the left and the plus on the right, and then that's valid, that's fine. Or you could compose the exponential here with 3 and then apply that as a top on the sum. But both of these are somewhat obscure, and they don't map very nicely to the original expression that we had. Now with the constant operator, we can preserve the order we had before, because we change the array as the right tine into a function. This becomes a valid train, and now we have function, function, function. That's fine, and we can read this still as the sum to the power of the constant 3. Here's a slightly more involved example. Here we are, instead of raising to the power of 3, raising to the power of the reciprocal of 3, or the cube root of the sum. And you would have to compose together the power with the reciprocal if you wanted this to work as a train, but it still wouldn't work because we end up with a constant on the right. And now the workarounds are even worse than before. We can't spell out the third because it can't be expressed exactly in decimal form. So we'd have to either parenthesize it, which means that you have a non-integer becomes part of your train, or as you on the last line, some really odd incantation that's very far removed from the original expression, not at all as clear. And until now, you might have said in this case, well, then don't use the tacit function for this one. It's not a good match. However, with the constant operator, then we can preserve the fidelity here to the original expression. We still have to compose the power with the reciprocal, but at least we can read this as the sum to the power of the reciprocal of the constant 3. Or we could insert a left argument to the division sign, and then we get the sum to the power of 1/3, which is of course the same. It's really nice and readable. Then I said you can avoid some otherwise ugly things. Let's say we have a job here. We have a mask and we have some data. And we want to use this mask in order to replace the indicated elements with the quad symbol. So traditionally, you might use a selective assignment like this, but the modern way, of course, is to use the at operator. So pretty simple, quad at, and then because we're using a mask here, so the at operator has these two different modes for the right operand. It can take a list of indices at which to replace, but that has to be an array, or it can take a mask, but that has to be returned from a function. So we have to have the mask here inside a function. And John Scholes, who invented this system, he said it's a type of quoting. You can see it, these braces, a type of quoting. Well, that's all very good, but let's make a utility function that does this. It takes a mask, and then it puts quads into those locations as indicated by the mask in the right argument. That looks fine, except we get a value error. What happened? Well, the inner braces, the inner defen, introduced a new scope where we have a new left argument, and the at operator doesn't supply any left argument to its right operand. We can't see the left argument of the outer defen because it's being shadowed over by the left argument or missing left argument of the inner defen. The solution to this is to use the constant operator. Because we're not introducing a new defen scope here with a new left argument or missing left argument, then we can immediately see the left argument of the outer defen. There is only an outer defen, but we still are fulfilling the requirement of the at operator to use a function to supply the mask. So that works. Alternative to this would be to either give the outer alpha a name, or you could compute indices and use that. Right. You might not believe me. It seems like it can do all these different things, but it's actually the simplest operator you could possibly write. This is all there is to it. However, if you would try to write brace alpha alpha n brace, then things might be really obscure. Using the proper symbol for the constant operator, that makes everything quite clear and readable, in my opinion. Okay, remember, this is a webinar, and you are allowed to ask me questions in the chat, and Richard Park is there on standby to convey the questions to me. I'll try to answer them. If you have any questions on this, please feel free to ask me now. Meanwhile, I'll continue with the next thing, and that is date and time. So we have two different features that are being added to 18.0 with regards to date and time, but they both deal with date and time as a concept, as a datetime. So a datetime just is a representation of a moment in the history. It could be as a timestamp, it could be as something we call a time number, and it could be as a military time zone. A timestamp you know already. You have this in quad TS. TS stands for timestamp. So the deal with a timestamp is that you have a vector of numbers that together represent a moment in history. However, there are other potential timestamps. It doesn't have to be year, month, day, hour, minute, second, and millisecond. For example, you could replace the milliseconds with microseconds or nanoseconds, or you could count, instead of months and days, you could count in weeks and which day of the week it is. So, this is the example of the time when, in British Standard Time, when this webinar started. Another way to represent it is a time number. Time number is a continuous counter from an origin or an epoch. And here we can count as, say, the number of whole days since the beginning of a time. But we could also count in the number of seconds or milliseconds or fractions of a second of some sort. All these scalar counters from a starting point, they're all time numbers. And we could even have a variation on it where it isn't exactly a counter, but some kind of encoding as a number. But as long as it's a scalar number that represents a moment in history, that's a time number. And finally, military time zones. It's not something that's universally known, and we've only added it really as a convenience. It also doesn't cover all the time zones in the world. But the idea is that that Zulu time, or universally coordinated time, is described with the character Z or Z for the Americans, and then we start counting up A, B, C for the whole hour time zones after that, and eventually count down from N, O, P from all the time zones before that. And then a special one, which is J or Juliet, which is a variable one that goes on whatever the local time is for the speaker right now. So my Juliet time right now here in London is A or alpha time, which is UTC plus 1. Of course, when we get to the winter, then Juliet will move one step up and become Zulu time. So this the alphabet nicely maps over the world map, and there are a couple of things you can see here. Possibly there are some striped areas on countries that have non-whole hour time zones. Some have half hours or even 45 minutes after a whole hour time zones. And if you're really keen-eyed here, you can also see that Y and M look like they're the same, namely the time zone that's by the international date line, and that is because some countries are a little bit beyond the date line and still use the date from the other side. So the time is the same for Yankee and Mike, but the date is different. And there are even additional hours beyond that, but they're not covered by the military time zones, just like the half and 45-minute ones are not covered. Juliet time is right now alpha. Over here. Looks like we're off by an hour from where we should be geographically, and that's true. That's what summertime is all about. We have a lot of formats. I'm not going to go through all of them now. But here are just some examples of them. And notice that I have bolded the first row, number 1, and the timestamps we use negative numbers to identify them, the negative one. That is because they are the default ones. I'll show you what I mean by them being default. There are lots of these. Look up in the documentation, put the cursor on quad DT and press F1, and you can get the whole list of them. There are lots, and we might even add more in the future. So, what is the syntax of this quad DT function? Well, it can do two things. It can do conversion of date times, and it can do validation of date times. And in each of those cases, you can use one or two codes as left argument, and then the right argument is just an array of one or more date times. And you should know, though, that since a vector can be a date time, that's a timestamp, then it has to be enclosed in order for it to be a single, taken as a single date time and not as a vector of time numbers. And so on the left, the full syntax of it is that we have the code that we just saw some examples of for that identifies what is the data that's coming in, what is it that's in the right argument, and then another code to what do you want it to convert it to instead. And if you don't supply the code identifying what's coming in, then we assume that any scalar is the first one, the bolded one, the dialog day number. And if it is a vector, then we assume it's a quad TS style. So you can omit that in those cases. You don't have to. Finally, if you choose 0 as the outcode, then we won't error if there's any problem with any of the given dates. Instead, we are going to return a boolean of the same shape as the right argument that shows a 1 for all the valid date times and a 0 for all the invalid ones. So that's a really neat way. You don't even have to convert any representation of a moment in history to know whether that's a valid moment in history or not. You can just supply the code for it and then say you want to check whether that's a valid date. Okay, here's some examples of that. So we take a timestamp, in this case when the webinar started, and and we want to convert it to type 20, which is Unix time, or the number of seconds since the beginning of 1970. And we can do a leap year check to see whether year 1900 was a leap year. Some people got that wrong. It was not a leap year. So it's very easy to check for leap years now. Simply try the 29th of February, and if that's invalid, then it's not a leap year. If it's valid, then it's a leap year. And here we have a conversion of the current time in Zulu time. So this is something people have asked for a lot. What is the current UTC time? We've always had the quad TS, but that's my local time. So in order to get the quad TS, but the UTC time, we say we convert, so to say, the Zulu time. It doesn't really matter which format it's in, because the letters, the military times, they just represent a time in a certain time zone with no particular format. So you can always use those in an array with other representations and convert that to type -1, which is the quad TS style. And I have a couple of questions. So let's see what's coming in. Meanwhile, here at the bottom we have we want to know which time zone am I in. So since we have the Julia time, the current time zone, and we have the Zulu time, the UTC time, then we can compare them. So we can compare them here, for example, in type 20, which is Unix time, which is seconds. Doesn't matter what the epoch is. Subtract the number of seconds divided by the number of seconds in an hour, and we can see that we are 1. We are currently here in London at UTC +1. Okay, so we have a question which is not just converting dates, but how do we do useful things like finding the beginning of the month, or adding a number of days to a date. Some of the things you can do with very slight added code here. One of the things that's really nice with the, for example, with the timestamp format, is that if you omit values in a timestamp, then we pad it out with the missing elements, and will default to the beginning. So the hour will begin with the 0th hour, and the month with the first month of the year, and the day with the first day of the month. And so you could find the beginning of the month simply by truncating the date, and then asking for it in a particular format, even the same format that it's currently in. You are allowed to convert from a format to itself. So some of the things you can do, adding weekdays, we can certainly add days. That's very easy. So you convert to a format that uses days, to say the default Dyalog day number, and then you add the days. However, if by weekdays you mean work days, that becomes much more complicated, because that would require it's not enough to just count the number of Mondays to Fridays. There could be holidays and so on. You'd really have to define what they are. But something kind of hidden feature of the Dyalog day number is that if you floor it and you take the division remainder with 7, then that will give you the day of week as a number from 0 to 6. So it's quite easy to get a range from a certain date, and then take the modulus of all the day numbers for those, and then figure out how many days you need to add in order to have work days. Right, ISO dates being asked about on slide 25. You can go back and see. Right, okay. So, yes, the idea here with it being an ISO is simply that the ISO standard specifies. It's not a format. It's just the ISO standard specifies how we number days of the year, how we number the weeks, which week is the first week of the year, and so that's what it means here, ISO. We'll come back to formatting later, and therefore it has nothing to do with the precision. It's simply a way of just storing the date. Okay, yes, I'm currently in summertime. Now for some examples with 2 elements as left argument. So here we are taking a Unix time and we're converting it to a quad TS style. And same thing here, we can directly check whether 1900 was a leap year, given this very special encoded format where the first 4 digits of an integer are the year, the next 2 digits are the month, and the last 2 digits are the day. So some people have stored dates like this, and that's format number 60. And we can check whether that's valid. We don't have to do a conversion first and then check. Okay, so moving on to formatting of dates, as I said, with regards to the ISO format, we'll get to that. So we've added it for now as an I-beam, the 1200 I-beam, and I'm sure you can guess why it is 1200 I-beam. I'll show you in a moment. The important thing about it is that it must take a dialog date number. So you have to convert to a dialog date number before you format. But other than that, it's really simple, obviously, to do that. Whatever type of date times you have, you do that code, and then a 1, that means convert to dialog date numbers, and then you're ready to feed it into 1200 I-beam. And the answer to why it's called 1200 I-beam is, of course, because that's what your alarm clock shows when you've had a power outage. Now, let's look at this format. That's the important part here. So the format is a character vector, and we looked around for various formats that other programming languages and systems use, and we weren't really happy about any of these. We wanted something that's plain obvious when you see it and easy to remember how to use, and all the ones we found had severe or some compromises in that. So and we also wanted to add some features that nobody else has. So if you look at Wikipedia on date formats, so then it uses this informal specification that's just so obvious you barely even have to explain it. That's what we were looking for. So, for example, this initial format we saw from Wikipedia, that just works. If you use this as a format, then this is what you get what you expect. And we also have some rules with regards to each pattern. So we have these subpatterns which are consecutive runs of the same character, and there are some rules that apply to that, and those rules are very general. So if you just learn about one of them, then you'll know them all, basically. So let's go through this pattern. Let's take the month as an example. So we can vary the number of m's. So a single m, that gives us the month number. If it has 2 digits, it will take up 2 characters. If it has 1 digit, it will be 1. If you use 2 m's, then we'll pad with a 0 on the left. If you use 3 m's, then we'll give you an abbreviated month name, and if you use 4 m's, we'll give you the full month name. This is pretty much exactly the same thing as you saw on Wikipedia. In there it was informal, but here it's formalized. In fact, it has one more little trick. Sometimes you want things to line up, but you don't want a leading 0. So we allow you to replace the first character when it is a numeric format with an underscore, and that will put in a space instead of a leading 0 if that's necessary. And of course, the names of months and days of the week vary from between languages. So we allow you to put in this tag, a doubly underscored language tag, which is the ISO language names, name abbreviations for the names. And we've built in quite a few languages already. One thing I won't go through here is the exact syntax for adding your own, but it's quite easy to add a dictionary to either modify an existing language or create your own language entirely. And so you can even switch language whenever you want. So if you're in a bilingual country like Finland or Canada, you could create a format that both has the English and the French, or Swedish and Finnish languages inside the same format. So every time you have this tag, then the language changes from there on. So as mentioned, a feature that nobody else has, that's the ability to do casing properly. So casing is a big theme in version 18.0, as we saw in the previous webinar that I had. So we allow you here, if you specify all uppercase letters, then it's all uppercase. If you specify all lowercase letters, it's all lowercase. So basically we allow you to draw a picture of what you want. And of course, if you want the initial capital, you can do that. And no, you can't put a capital in the middle of the name. That won't work. And that of course works across languages. Now you may not know that there are some different conventions as to how to spell the names of months and weekdays across languages. So in English we always capitalize the name of months and days, except maybe if it's inside a URL or a hashtag or something like that. But in say French or Danish, it's only capitalized in the beginning of a sentence. Or say if you have a title, that's all uppercase or something like this. And you couldn't go and look up the convention of every language, but as an added convenience to you, we allow you to replace in patterns that specify a name. You can replace the first character, which could be uppercase or lowercase, with an underscore, and that will do a proper casing for placement inside a sentence. We couldn't just always do that because maybe you're in the beginning of the sentence and you want it to be uppercase. So then you specify an uppercase first letter in the pattern. Furthermore, you might want to have a fancy format that put on special ordinal markers you have in English for the first and second and third. And we can do that with the O. And of course, O representing some text, you can change the casing of that as well as you please. Now English, you always add 2 letters, but in some languages it's different. So in French, on dates you only add the ordinal indicator on the first of the month. So if you specify the ordinal, then we make sure that it's blank for all the dates that don't need this. And again, you can use single and letter as well. That will chop it to just the first character if that's interesting. In Danish, it's not 2 characters. So then, even though you specify 2 O's, it will just print that one period, full stop, that indicates an ordinal. Or you could just put in a literal dot in your date format. That will work fine for Danish as well. Some people like using 12-hour clocks instead of 24-hour clocks, and so we can use a T instead of an H for that. You might have noticed a pattern here, also something that's unique to Dyalog's format, and that is that all the numbers that relate to the date are all uppercase, and all the numbers that relate to the time are lowercase. So it kind of indicates the big end and the little end of the date time. The date is uppercase and the time is lowercase. Makes it easy to remember. Whereas many other languages have a mixture, a jumble of uppercase and lowercase letters for various things. And so you can put in an AM PM marker if that's appropriate for your language. Most languages don't have that. And of course, that being text, you can change the casing and spacing of that as well. Here are some examples of this, some formats you might want to use. And you can really see here how the pattern you have to use draws the picture quite precisely of the result that you're going to get. Also seen here is the way to insert random text into your pattern. Of course, the Latin letters having special meaning, you can't just put in other Latin letters to have the text inserted, but you can quote them in single quotes or double quotes. And just remember, for the odd case where you need a quotation mark, whether single or double, inside your pattern. It just needs to be doubled inside the other quotes. And finally, as I promised, ISO format. There are actually a lot of different ISO formats. And again, just like you can define your dictionaries, you can also define these patterns. So we've defined one for you, which is the %ISO%, and that just expands to the expanded ISO format for just a date and time. However, there are many variations on this, and there is no real naming convention for these various formats. So we've bundled this one, as this is a very common standard one, but it's very easy for you to predefine these patterns that you can then use inside other patterns. And there are a few more tricks to 1200 IBeam. If you open the documentation for IBeam, you can find 1200 on it, and then go in there and see all the fancy things that you can do. But that is what I'll go through here with this. So, this was a whirlwind of constant and date time and format date time. If there are any further questions, now is your chance to ask. Okay, that is what I wanted to go through today. However, there are a lot more features in 18.0, and I will continue in 4 weeks with the third webinar in my series here of new language features for version 18. So we have a question how to get Roman numerals out of this thing. That's really funny actually, because immediately after we released 18.0, I kind of in jest suggested to Richard Smith, who had been the one implementing this, that a way to put Roman numerals into it. There currently isn't that any way to make it produce Roman numerals. You would have to use a numeric format, and then there's a function in the defense workspace, for example, to convert numbers to Roman numerals and then insert them there. However, it's very likely, if people actually want this, let us know, and we might add Roman numerals and maybe even other numeric forms to the system. Again, this formatting datetime, it is an IBeam, which means it is somewhat experimental. Remember to put it in a cover function if you use it. We may turn it into a real system function, or maybe even roll it into quad_dt one day. Notice that quad_dt takes a numeric left argument, and this format datetime takes a purely character left argument, which means they're actually designed to be compatible, that the format datetime can be rolled into quad_dt in the future. But that is it for me. I'll be joining you in the chat momentarily. Until then, there is in 2 weeks another webinar by Richard Park, which starts another series of thinking in APL. Thank you so much for watching.